All right, so in this video, I'm going to talk about production externality, a simple model of production externality. It's going to be a negative externality because the externality is going to be the pollution. And I'll talk about what it means internalizing externality and how it could lead to efficient allocation. All right? And then in the next video, I'm going to solve a numerical example. So this is going to be theory. And then in the follow-up video, a numerical example. So here I have two agents, all right? Two agents, two firms in this case, firm S and firm F. So firm S produces steel and firm F produces fish. Right? So it's a fishery, the steel company. Well, the firm S produces steel, the small s, the amount of, the number of steels produced. And then as a side product, it also produces pollution. So X represents pollution, X represents the steel. Well, therefore, that means the steel company has two variables to choose. Steel on the one hand and the pollution on the other. Both of those affect the profitability of the company. And I'll talk about the profit functions. Well, the pollution is something that you don't get profit, but it costs you. All right, so that's sort of the idea. I mean, you don't sell pollution, you just dump it on a river. Let's say this steel factory is next to a river, and so you just dump the pollution. So you generate pollution, but you don't really earn revenue from the pollution. But it influences your cost because reducing pollution is a costly action, all right? Well, you have to clean up the water that you polluted before dumping it to the river. You have to use some high-tech filtering system, more energy, more whatever, manpower maybe. So cleaning the pollution or reducing the X is going to be costlier, all right? So that's sort of the idea. The firm F, the fishery, produces fish. The number of fish it produces is going to be denoted by small f. And the fishery is located downstream. So there's a river, all right? So the stilling company is here and the fishery is here. So the stilling company dumps the polluted water. So this is how the river. So then there's a lake or sea, whatever. So this polluted water basically goes through the fishery. And so the fishery, the fish producer has to use water which is already polluted by the steel producer, all right? So here, what we assume is that these two companies have, our price taker. So the price of steel, as I said, there are two variables. Oh, the fishery has only one variable. It only chooses how much fish to produce. It can't produce how much pollution sort of kicks into the... So the fishery does not have the technology to clean the water, for example. All right, so we just simplify. So X is a choice variable only for the steel company. The fishery has only one choice variable, which is how many fish to produce. Again, this is a very simplistic model. This is a general equilibrium model. All right, these are two firms, but we're not really talking duopoly model. We are in a perfectly competitive, a general equilibrium model where we have two firms and they take their prices as given, let's suppose. For simplicity, again, it's like making the price choices as a strategic choice will just complicate the problem, all right? So let's make it simpler. So these are taking the prices as given. So the PS represents the price for steel and PF represents the price for fish, all right? And what are the other question or model specific assumptions? Well, the cost functions. The steel company has a cost function which depends on the number of steel it produces and the amount of pollution it produces. And then the fishery also has a cost function which depends on the number of fish it produces and at the same time the amount of pollution it has to go through. So this is again a model-specific assumptions that we make. Well, what else? As usual, the cost functions are going to be increasing with S. I mean, the marginal cost of production is, well, either increasing or constant with S. And the marginal cost of fishery is also increasing or constant. Oh, yes, this is not S, I'm sorry, this is 0. So I mean, it's positive, so it's increasing. So the more you would like to produce, the more costly the production will be. So this is a general, standard assumption. The other kind of standard assumption is that the fisheries cost function, all right, also, so del CF, so the marginal cost of fishery with respect to pollution is also, well, let's make it positive, all right? Because we're now talking about externality. So if it was 0, it means the pollution doesn't really change your cost. And you'll see it's not going to change your revenue, so therefore it's not changing your profit. Well, if it is not changing your profit, it means the action of one company does not influence the path of the other, and hence there is no externality. So in order to talk about externality, that thing has to be positive. But it shouldn't be negative. Why? Well, the more polluted the water is, costlier the production for you is going to be. So, well, why is that? Well, because as the water is more polluted, more fish will die, all right? And hence, the final output, the same amount of final output, that means you have to give up much more dead fish, and so that's going to raise your cost function. All right, so think it this way. So the cost of production increases as well for the fishery as the pollution increases. Here, the key assumption is that the marginal cost of the steel company, yes, this is the steel company, with respect to the pollution, however, is less than or equal to 0. All right? Well, in order to make sense, we're going to assume that this is strictly less than 0, obviously. If it is 0, it means it doesn't change your cost function. But the thing is, it's not positive. Once again, the intuition is the following. The more the pollution is, means the less cleaning you're going through, and therefore your cost is going to be less, right? So the more waste you dump means you don't really have to do any cleaning. You just dump all the pollution you're generating. And so your cost is going to be minimum when you can dump all the pollution you produce. Your cost will increase as you try to sort of dump less and less pollution, because you have to go through cleaning and everything. And so the cleaning is costly. All right, so therefore there's a negative relationship between pollution and the cost. Okay? So that's it. These are the model-specific assumptions. That are two agents, steel company, fishery. The prices are given, the cost functions are given, and the marginal costs are increasing, but the marginal cost of pollution for the steel company is decreasing. All right? So, if this is the case, well, what is the problem? Well, the optimization problem is the following. Well, these two agents are, well, first of all, there's no market for pollution, let's suppose, so they can't really trade. Okay. And then second thing, let's suppose this is usually the standard. So these two firms are two separate firms. So there's a steel company, there's a fishery. They are owned by different people, and they only care about how much profit they will get. All right, and independently choosing their variables. So therefore, the optimization problem for the steeling company is to maximize its own profit by choosing those two things: the number of steels to produce and the number of pollution to dump. Well, what is the profit function? As usual, the profit is very simple. Revenue minus cost. What is revenue? They take the price of steel fixed. So P of S times S. So that's revenue. Remember, the steel company cannot make profit out of dumping pollution. So that's it. That's the revenue. Minus the cost, right? The cost of producing steel and pollution. So what is the optimization problem for the fishery? Well, it's only choosing the number of fish to produce to maximize its own profit. And its profit is, again, simple, revenue minus cost. And the revenue here is price of fish times the number of fish you produce. And that's it. That's your revenue. Minus your cost of producing F and given the X. So X is not a choice variable. You take the X as given. Okay? So here, the fishery only chooses F. So its decision problem is simple. To maximize the profit by choosing F means the first order condition for steel company, it's basically del pi S del S, which is equal to 0. And then del pi S del X also equal to 0, and solve for those two. All right? And for the fishery, the first order condition is del pi F del F equals 0, and solve for that. So when you solve these two first order conditions, or the first order conditions, well, the derivative with respect to S is PS minus del CS divided by del S equal to 0, right? And the 0 also equals to the derivative with respect to X. So the derivative of the revenue with respect to X is just 0. So it's minus del CS del X. Okay? So therefore, if you solve these two first order conditions, let's call I send the marginal cost to the other side. So therefore, the price has to be equal to the marginal cost of the steel company, and then the X star and S star should be such that, well, I should put the S first. That doesn't matter, but just let's be consistent in notation. So S star, X star. So del S. So the price of the fisher as steel has to satisfy this inequality, this equality. So the S star and X star should solve this equality. And at the same time, we have this equality, which is the minus and the 0, right? The minus is going to go. So what we have is the marginal cost with respect to pollution. The value is, again, S star, X star, has to be equal to 0. So the X star and S star should satisfy these two conditions. All right? Well, what about F star? I mean the optimal. So X star and S star are the optimal amount of steel and optimal amount of pollution the steel company will produce. Well, what is the optimal amount of fish the fishery will produce? Well, for that, you have to solve the first order condition for the fishery, which is, if you take the derivative of the profit function of the fishery with respect to F, you're going to get PF minus the marginal cost of the fishery with respect to F. So equals to 0. So if you solve that, meaning it's going to be PF equals, right? I just send this to the other side, del CF del F. Here I have, say, F had, star and X star. So this X is not a different X. So we have to have this equality. So there are three parameters that we need to solve: X star, F star, and S star. And those three parameters must satisfy these three equations. Okay? So whatever the value of F star, X star, and S star that solves those three equalities, is going to be the solution of these two independent optimization problems. So what we know is that so this is not going to be pretty efficient, most probably. So how do we find the pretty efficient one? So let me erase those. Well, in order to find the pretty efficient, well, there are many, right? Infinitely many potentially pretty efficient allocations in this problem. So one of the pretty efficient allocations is the one, remember, in the previous chapter we said any allocation, the allocation that maximizes the social welfare function is going to be pretty efficient. All right. So, question is, what should be the social welfare function? Well, let's use the standard utilitarian social welfare function. I mean, we simply add both firms' profit function and then maximize it by choosing S, F, and X. All right? So you can imagine this as like, oh, these two firms, the fishery and the steel company, are not two independent firms. They are actually owned by the same guy, same owner, and that owner would like to maximize the total profit by choosing those three parameters. All right? So rather than individually maximizing profits, because they both are collecting money into the same vault, the owner is now trying to maximize the total profit. Well, is it going to give me a different outcome? Yes, it will be. All right? Theoretically, at least. How so? Well, if you want to solve this optimization problem, well, remember the total profit this time is basically this plus this. All right? So let's write it. So the total revenue, which is PS times S plus PF times F, minus the costs, CS SX minus CF FX. All right, so that's the total profit. So how do I solve this optimization problem? Well, the first order conditions, meaning the derivative of the pi with respect to S and the derivative of pi with respect to F and the derivative of pi with respect to X, they all has to be equal to 0. And therefore, I have to solve those three equations. I will have three equations once again. So let me clean up a bit. I'll just leave those terms in parentheses because I'm going to make a comparison. All right. Don't forget that those parentheses are actually the optimization problem outcomes. So F star, X star, S star, and F star, which basically maximize the individual firm's profits. Now I'm maximizing the joint profit. So once again, what is the derivative with respect to S? Well, it's going to be the price of steel. The derivative with respect to S is just 0. The derivative with respect to S is minus del CS del S. So the fishery's cost function doesn't depend on the steel because the fishery doesn't use or produce steel. All right? So therefore, this is equal to 0. The partial derivative with respect to F is going to give me the derivative of this thing with respect to F is 0. The derivative of this thing is just PF minus derivative of this thing is also 0 with respect to F. And the derivative of this thing with respect to F is the marginal cost of the fishery. So it's equal to 0. And then finally, the derivative with respect to X. So the revenue doesn't depend on the pollution. Only the costs will depend. So it's minus del CS del X minus del CF del X equals 0. So let's just rearrange them. If you just send these guys the marginal costs to the other side. I have PS equals marginal cost of the steeling company. And then PF equals the marginal cost of the fishery, all right? And then the marginal cost of pollution, the total marginal cost of pollution is equal to 0. Okay? So these three, these cost functions now depends on S and X. This depends on F and X. And, again, they depend on SX and FX. But this time, I am looking for the optimal S and X and F that satisfies these three equations. So they are going to be different than star, right? So let's call them hat. F hat, X hat, S hat. So the same thing here. I'll just not write it because I have already cramped a notation there. So let's compare these three equations with those three equations. So how are they different? Well, the optimal S and X should solve these, this versus this. So it's the same, right? The marginal cost of steel equals to price of steel. So it's the same across these two solutions. All right, what else? The marginal cost of fish is also equal to the price of fish. So that's also the same. What's different is that the marginal cost of pollution for the steeling company is equal to 0. This term is 0. However, this optimization problem says, oh no, this doesn't have to be 0. This sum must be equal to 0. And in fact, this thing equals to 0 is, unfortunately, I erased this. If you remember, we already assumed that the cost function of the steeling company with respect to X was negative, right? If you remember. So if it is strictly less than 0 means the higher the X, the lower the costs are. So therefore, this equality will never hold, in fact. So what does that mean? Does that mean that the S star and X star will never exist? No. If the marginal cost is negative, it means you should choose the pollution level as high as you can, because as you increase the pollution, your cost is decreasing. So therefore, the optimal X star is equal to the maximum pollution you can create. Well, if it is infinite, it's infinite. If it is finite, well, because the pollution will probably be a function of the steel that you produce. So therefore, whatever the maximum pollution is, well, that is the optimal pollution. So the steeling company actually doesn't care about how much pollution it generates. It's just going to try to keep it as high as it can be. However, when it comes to this sort of aggregate payoff optimization, well, then this thing is, as we know, negative. So yes, you would like to keep X as high as you can, but you know what? This thing is positive. So if I increase X, I'm going to decrease this, but if I increase X, this is going to increase. So on the one hand, I am decreasing the cost by increasing X, but on the other, I'm increasing another portion of my cost function. So I decrease the cost, but I also increase my cost. So what matters is that I have to balance them out, all right? And then I should choose the X optimally in such a way that my total marginal cost, let's call this total marginal cost, is exactly equal to 0. So therefore, the solution here is going to be different than the solution there. So the solution here, the XF, is not going to be, obviously it depends on the cost functions, the specific cost functions, but it's not going to be X star, all right? And in fact, I think it's already intuitive that this is not going to be Pareto efficient. Why? Well, because the steel company doesn't care about the profitability of the fishery. It just dumps all the pollution. Dump it, because it's cheaper. All right, but the more and more pollution is dumped, well, the fisher's profit is going to sink. All right, so the total profit will sink. So when you try to maximize the total profit, you're going to choose the pollution optimally, because you also not only care about the steel company, but also care about the fishery. You also try to fishery's profit as high as you can. All right? So this is what we call internalizing externality. All right? And this outcome is going to be efficient by the first theorem of welfare economics. So therefore, in the equilibrium, the steel and the pollution and the fish is going to be such that those three first order conditions are satisfied. And it is going to be Pareto efficient by the first theorem of welfare, first fundamental theorem of welfare economics. And this is going to be inefficient, but as I said, intuitively it makes perfect sense, because here one firm is acting individualistically and doesn't care about the other firm's profitability. And here we try to maximize both firms' profit at the same time. And hence we get a different result. So this is efficient, this is inefficient. And yeah, I hope that was clear. Let's give a numerical example and see that in fact the outcome here we get is going to be efficient and the outcome we get here is going to be inefficient. Okay?